Welcome to the debate. Imagine you have spent like 5 years and $5 billion building an orbital toll booth in deep space. You have international partners delivering modules, contractors finalizing the wiring, and, well, years of political capital invested.
Right.
And then, right before it launches, the new director walks into the room, looks at the blueprint, and just says, "Scrap it. We are building a $20 billion city on the surface instead."
I mean, wow. It is the exact kind of pivot that gives congressional budget offices absolute nightmares.
Exactly. But, that is exactly what just happened at NASA. We are here for the third installment in our Artemis series analysis, and we are diving into the sweeping overhaul of the Artemis architecture under NASA's new director, Jared Isaacman. This is just a massive structural pivot.
Yeah, it really is.
We are talking about the outright cancellation of the Lunar Gateway, that orbital space station I just mentioned. In its place, the establishment of this Ignition lunar base project targeted for 2030, and, of course, a deeply aggressive reliance on commercial partners, most notably that NASA and SpaceX deal led by Elon Musk.
A pivot that, honestly, completely rewrites the timeline. It fundamentally alters the physical hardware we are relying on to, keep humans alive in a vacuum.
It really does. And so that brings us to the central question we're exploring today. Do these massive financial investments, these radical architecture overhauls, and this heavy reliance on commercial mega contracts actually improve the probability of mission success and inspire the next generation of scientists?
Or, on the flip side, are the ballooning cost and continuous timeline shifts fundamentally undermining the viability of our return to the moon at all?
Right. And we are grounding this analysis in the recent programmatic, financial, and technical reports surrounding the Artemis architecture. I will be arguing that this pragmatic overhaul and the reliance on commercial iteration actually creates a sustainable, highly probable path to lunar infrastructure, a path that will profoundly inspire new scientists.
And I will be arguing that the astronomical costs, the systemic bureaucratic inefficiencies, and, well, the deep reliance on unproven commercial hardware are critically jeopardizing the actual probability of mission success.
So let me start by laying out my position on why this shift is not just necessary, but genuinely visionary. For decades, we have been constrained by a legacy aerospace mindset, right? The idea that you have to get everything perfect before a single vehicle leaves the launch pad.
Well, when lives are on the line, yeah.
Sure, but shifting Artemis 3 to a 2027 low Earth orbit docking test, while targeting Artemis 4 and 5 for the actual lunar landings in 2028 is a highly calculated move. It is designed to increase the probability of mission success. By leveraging commercial innovation, specifically the $4 billion SpaceX Human Landing System, or HLS, alongside Blue Origin's lander, we are finally shifting the paradigm.
Shifting it to what exactly?
To sustainable, reusable infrastructure, rather than single-use, expendable government rockets. And when we look at the new $20 billion Ignition base and the historic diversity of the Artemis 2 crew, which includes Christina Koch, these are vital, tangible investments in the STEM pipeline. We are moving past the flags and footprints of Apollo to inspire a completely new era of extraterrestrial field science.
Look, I understand the appeal of the vision, I really do. But let me tell you why I simply do not buy that this is a pragmatic or probable path forward.
Okay, let's hear it.
The financial and logistical realities of this program are just alarming. We are looking at an estimated $93 billion spent through 2025, and we have not yet put a single human boot on the lunar surface.
Space is hard. It takes time.
It does, but the SLS rocket is currently costing taxpayers $4 billion per launch, and this visionary pivot you were talking about includes canceling the $5.3 billion Lunar Gateway project right in the middle of its development. Physical hardware was literally being built.
It was a necessary cut, though.
But international partners are left holding the bag. That highlights systematic mismanagement to me. Furthermore, the probability of success is actively hindered by relying on delayed commercial systems. SpaceX's Starship is far behind schedule.
They are iterating quickly, though.
But those delays are the direct cause of the Artemis 3 downgrade from a landing mission to an orbital test. It is incredibly difficult to inspire the next generation of scientists when timelines constantly slip, Budgets run 140% over projections, and the core vehicles just keep failing to meet their milestones.
I appreciate the hesitation regarding the budget and the schedule, I do. But let's look at the hardware reality from a different angle, specifically regarding the probability of mission success. You just called the shift of Artemis 3 a downgrade.
Because it is. We aren't landing on the moon anymore for that mission.
I look at it as a necessary maturation of the risk profile. We have to acknowledge that deep space exploration is inherently fraught with peril. NASA's overall crew loss threshold right now is 1 in 40 for lunar missions.
Right.
Compare that to the Apollo era, where the accepted risk of crew loss was roughly 1 in 10. By pushing the SpaceX and Blue Origin testing to low Earth orbit first in 2027, we are actively increasing the ultimate probability of a safe lunar descent.
Okay, but pushing it to low Earth orbit doesn't change the fact that the hardware currently sitting on the pad is struggling with basic physics.
What do you mean?
Let's talk about the fragility of this mission architecture. We watched Artemis 1 launch 3 years ago, right? We saw hydrogen leaks, we saw helium flow issues.
Yeah, minor issues that were resolved.
But then Artemis 2 goes out to the pad for its wet dress rehearsals, where they actually pump it full of super chilled fuel to see if the plumbing holds under pressure. And what happens? More hydrogen leaks.
To be fair, hydrogen is notoriously difficult to manage.
It is a nightmare to manage. We have to remember why hydrogen leaks are so persistent. Liquid hydrogen is the smallest molecule in the universe.
Exactly.
And to keep it liquid, it has to be maintained at minus 423 degrees Fahrenheit. It will find microscopic gaps in seals that shrink and warp from the extreme cold. You can't just patch that easily.
They're working on permanent fixes.
But launching a vehicle as complex and temperamental as SLS every 3 years is simply not a viable path to success. But honestly, the real terrifying reality isn't the propulsion, it is the Orion heat shield.
Well, the heat shield on Artemis 1 did perform its primary function, which was getting the capsule back intact.
But look at how it got it back. An ablative heat shield is designed to slowly char and flake away, burning off the kinetic energy of reentry in a very predictable layer.
Right, that is how ablation works.
Instead, the Orion shield unexpectedly cracked and splintered. It broke off in massive chunks. It shed material in a way the engineers did not model at all.
Which is why we do uncrewed tests.
But shedding chunks like that dangerously alters the aerodynamics of the capsule at Mach 32. And rather than completely redesign and replace that heat shield, NASA is just reusing that design for Artemis 2 with an altered reentry profile to try and mitigate the damage.
They believe the altered profile is sufficient.
That is an astonishing acceptance of risk for a capsule carrying 4 human beings. We have John Honeycutt, the SLS program manager, giving a stark assessment that Artemis 2 faces anywhere from a 1 in 2 to a 1 in 50 chance of failure. Those are coin toss odds on the bad end of the spectrum.
You are raising entirely valid points about the engineering hurdles of Orion, but I think we are fundamentally disagreeing on how engineering development should actually work in the 21st century.
How so?
Particularly on the commercial side with the SpaceX deal. Think about the traditional monolithic aerospace approach of the Apollo era. You built a bespoke, multi-million-dollar vehicle, and you tried to get it absolutely perfect the first time, because failure meant the whole project died.
Right, because failure was catastrophic.
But what SpaceX is doing with Starship, and what NASA is embracing by restructuring this contract, is essentially the software beta testing model applied to orbital mechanics.
Okay, help me understand this though. Rockets aren't software. A bug in a line of code gives you an error message on a screen.
True.
A bug in a Raptor engine gives you a giant crater in South Texas.
Exactly. But in an uncrewed test flight, that crater is just data. It is messy, it is highly visible, and it invites exactly the kind of criticism you are giving it right now.
Because they keep blowing up.
But failing fast and iterating quickly ultimately produces a more hardened system. You have to look at the physical reality of what SpaceX is doing. They aren't building one pristine rocket.
No, they have a whole fleet.
Right, they build an assembly line of 10 starships, fully expecting the first 3 to just explode. When one explodes, they look at the telemetry and they can instantly swap out the physical valves or reinforce the bulkheads on rocket number 4.
I get that. But the sheer complexity of what they are trying to achieve with the Artemis 3 low Earth orbit test is just staggering.
It is staggering, which is exactly why the LEO test is vital. The Starship HLS doesn't just need to launch and land, it requires an incredibly complex sequence of orbital refueling, utilizing fuel depots.
Which we have never done.
Right. We have never done cryogenic fluid transfer at scale in space.
And we should explain why that is so incredibly difficult. It isn't like pumping gas at a station. In zero gravity, super-chilled liquid oxygen and liquid methane don't just settle nicely at the bottom of the tank.
No, they float around.
They float around in globs. They boil off into gas from the heat of the sun. To transfer that fuel, you have to execute complex ullage thrusting, basically firing small thrusters just to push the liquid to the bottom of the tank so the pumps can grab it.
Exactly.
Doing that ship to ship at orbital velocities with dozens of tanker flights, it is a logistical tightrope.
Which proves my point perfectly. Expecting that to work flawlessly on the first try, 250,000 miles away in lunar orbit, would be completely reckless.
Well, yeah.
Testing it rigorously in low Earth orbit first, allowing SpaceX to use their iterative assembly line to fix the bugs when things inevitably freeze up or boil off, that is exactly how we ensure that 1 in 40 crew loss threshold is maintained. We are buying down risk.
Okay, but even if this trial and error beta testing works for the hardware, it is an absolute disaster for the balance sheet. Every time one of those beta tests blows up, or every time a massive engineering hurdle delays the timeline, billions of dollars just vanish.
It's part of the development cost.
How long can the taxpayers fund Elon Musk's learning curve? If these vehicles are struggling, we have to ask if the exorbitant cost is justified by the scientific return and the inspiration we are supposedly generating.
I think it absolutely is.
The United States is facing an immense federal debt, hovering around $38 trillion. Against that backdrop, spending $4 billion for a single SLS launch is economically indefensible.
Well, hold on. The $4 billion figure is the legacy cost of an outdated contracting model, which is exactly why the overhaul is relying on competitive commercial rockets moving forward to lower that baseline.
But the SLS is still the backbone for getting the Orion crew capsule to orbit for these upcoming missions. NASA hasn't replaced that. And let's look at the mid-scale infrastructure we have just thrown away.
You mean the Gateway?
Yes. The Lunar Gateway was a $5.3 billion project. It wasn't just paper. Thales Alenia Space was literally finishing the HALO module, the Habitation and Logistics Outpost.
Right, the staging ground.
Exactly, which was supposed to be the staging ground for lunar descents. We had international contributions from the European Space Agency, JAXA in Japan, the Canadian Space Agency. Now, Isaacman cancels it and says we are repurposing those contributions into the new surface-focused ignition project.
Because it makes more sense.
That is a very polite, bureaucratic way of describing billions of dollars in wasted development and alienating our global partners. By the time we hit Artemis 4, we are staring down a $105 billion price tag. How does that serve the scientific community when basic payload delivery timelines keep slipping into the next decade?
It serves the scientific community because we are finally aligning our budget with our actual long-term goals. Administrator Isaacman has been very clear about the financial philosophy here.
Which is what?
NASA does not have a top-line funding problem. The agency receives a tremendous amount of resources. What NASA has had is an allocation problem.
An allocation problem.
Yes, the Gateway, as much as I respect the engineering behind the HALO module, was increasingly looking like a moondoggle. It was an orbital toll booth. You had to spend fuel to get to it and spend fuel to leave it, and it just soaked up funding without putting a single boot or instrument on the lunar regolith.
It was a staging point for deep space.
But cutting Gateway and redirecting those funds into the $20 billion ignition project solves the allocation problem by putting the money where the gravity is.
By abandoning our international partners and throwing away years of precise, bespoke design work.
Look, the partners aren't abandoned. Their hardware and life support contributions are being repurposed for surface habitats and pressurized rovers, which is where the real science happens.
Assuming we get there.
And regarding that overall $105 billion price tag, We desperately need some historical context here. That number sounds staggering, sure, but if you adjust the Apollo program for inflation, it costs roughly $290 billion.
Different era, different goals.
We are achieving a permanent, sustainable surface presence for a fraction of that cost. And, more importantly, this investment creates a giant feedback loop for the STEM pipeline.
I'm sorry, but you cannot inspire a generation of scientists with a program that collapses under its own financial weight before it even achieves its goals.
But if it succeeds, the inspiration is unmatched. Let's talk about what the ignition base is actually going to do. When a student today sees Christina Koch orbiting the moon on Artemis 2,
that will be amazing, yes.
or when they see the plans for the ignition base extracting actual water ice from the permanently shadowed craters of the lunar South Pole, water that can be split into hydrogen and oxygen for rocket fuel, that is deeply inspiring.
It is cool science, definitely.
But it goes beyond geology. One of the most incredible scientific payloads planned is the radio telescope array on the far side of the moon.
To listen to the early universe?
Actually, to listen to Earth.
Really?
Think about this. Earth's magnetic field acts like a shield against the solar wind. And as it deflects that deadly radiation, the magnetic field emits a specific low-frequency radio wave.
Okay.
But down here on Earth, our own human radio noise is far too loud to hear it. Because the far side of the moon blocks all of Earth's messy terrestrial static, we can listen purely to that magnetic broadcast.
Oh, wow. I see where you're going with this.
Right? If we know what a life-protecting magnetic shield sounds like here, we can turn those telescopes out into the galaxy, scan for that exact same frequency, and find habitable exoplanets. Discovering another Earth because we built an observatory in the quietest place in our solar system?
That is incredible, I admit.
That is going to inspire a new generation of scientists far more than an orbital way station ever could.
Look, that is a phenomenal scientific objective. Truly, the exoplanet magnetic broadcast is the kind of aha moment that defines a generation. But you keep mentioning this $20 billion ignition base and these lunar farside arrays as if they are a done deal.
They are the plan.
Do you know what phase 1 of ignition relies on to get that equipment to the surface? It relies on commercial lunar payload services to deliver materials.
Which are scaling up now?
It relies on the very commercial systems, like the Starship HLS, that are currently blowing up on the pad or slipping their schedules by literally years. We are projecting semi-annual crewed landings by 2028. That timeline is completely divorced from the physical reality of the hardware production rates we are seeing today.
Let me challenge that perspective directly. I think we are falsely equating cost efficiency with scientific value. We are looking at a $30 billion permanent infrastructure plan when you combine the early phases of ignition and the commercial lander contracts.
That's a huge bill.
I prompt you to consider this. If that investment allows us to establish an enduring human presence capable of semi-annual landings and massive cargo deliveries by 2028, isn't that actually a bargain?
If it works.
We aren't just planting flags and leaving footprints like we did in 1972. We are building a sustained ecosystem. Starship alone can deliver 100 tons of payload to the surface in a single trip.
When it flies.
No legacy vehicle in development can even touch that payload capacity. If we have to wait an extra year or two for SpaceX to refine the cryogenic fluid transfer, the sheer volume of scientific instruments we can land makes the wait entirely worth it.
It is only a bargain if the system actually works, and if the political will sustains it through the failures you claim are just beta testing.
Political will is always a factor.
If a Starship HLS fails to transfer that liquid oxygen in orbit, or if the Orion heat shield chunks off and fails to protect the crew during the Artemis 2 re-entry, the political fallout will shatter this entire ecosystem.
Which is why we test.
You are betting the entire future of human spaceflight on the premise that these massive commercial mega contracts will eventually deliver on their promises, despite the fact that they are currently billions over budget and years behind schedule.
It's a calculated risk.
The risk here isn't just financial, it is existential for NASA's human exploration mandate. If we spend $105 billion and fail to maintain a safe, reliable cadence, the resulting congressional cuts will end deep space human exploration for another 50 years.
But the risk of doing nothing, or continuing within unoptimized, linear architecture that launches a $4 billion rocket once every 3 years is just as existential. If we don't innovate, we stagnate.
But we have to be smart about it.
The Isaacman overhaul injects vital urgency and commercial viability into the program.
Urgency shouldn't mean rushing unproven hardware to the pad or ripping up international agreements to chase a new 2030 lunar base deadline that is almost certainly a mirage. We need to focus on the basics first.
Like what?
Prove the SLS is reliable without leaking microscopic hydrogen everywhere. Prove the Orion heat shield is actually safe for human re-entry. Prove that commercial landers can manage cryogenic boil-off and land autonomously before we start drawing up blueprints for nuclear reactors and exoplanet observatories on the lunar South Pole.
And that is exactly what the Artemis 3 low Earth orbit test is designed to do. Prove the orbital mechanics and the life support systems work before we commit to the descent.
We will see if they actually manage it.
As we wrap up this discussion, I want to summarize where I stand. I firmly believe that the commercial partnerships, the strategic overhaul by Director Isaacman, and the pivot toward the ignition base represent a highly probable, deeply inspiring roadmap.
And a very expensive one.
Yes, it is a messy, explosive process. But integrating the agile assembly line iteration of companies like SpaceX with NASA's deep institutional knowledge is the only way we achieve sustainable lunar science and establish a true, lasting foundation for Mars.
And I maintain that the sheer cost, the rapid bureaucratic pivots, and the heavy reliance on behind-schedule commercial hardware present critical, perhaps insurmountable risks to the mission's actualization.
We definitely disagree on the severity of those risks.
You just cannot build a sustainable lunar base on a foundation of delayed rockets, leaking plumbing, and 140% budget overruns. The vision of scanning for exoplanets is grand, but the execution is currently threatening the very viability of the program.
Well, I think where we absolutely converge today is on the fact that the stakes for the upcoming Artemis 2 flight are just monumental.
Completely agree.
The telemetry that comes back from that mission, particularly regarding the performance of the Orion heat shield and the environmental life support systems, will dictate the physical and political reality of everything that follows.
Agreed. And, if the technical hurdles of the commercial landers are ultimately overcome, if they can figure out how to manage that super chilled fuel in zero gravity and perfect the descent mechanics, there is no denying that the scientific data returned from the lunar South Pole will be paradigm-shifting for planetary science.
It truly will be, and that reflects the deep value of examining these complex, multi-billion-dollar architectures through both an inspirational and a highly critical lens.
Absolutely.
There is still so much more to explore regarding the specific scientific payloads planned for these missions, which we will tackle in our future discussions. But for now, we leave it to you to decide whether the Artemis overhaul is a visionary leap forward or a costly stumble.
Because at the end of the day, when you rip up the blueprint for an orbital tool booth to build a lunar city, you still have to prove to everyone that the rockets can actually fly.
Exactly right. Thank you for joining us on The Debate.